Hello, this is Takeshi, and today I am going to be going over principal component analysis and how to do it as simply as I know of in Python. Principal component analysis identifies the direction of greatest variability in a multivariate dataset and simplifies it according to the direction of greatest variance. To do this, we define first empirical orthogonal functions, which are vectors which point along those directions of greatest variability in your large data set, um, uh, which essentially redefine a new axis for the data set to be built on. To start, we're going to need to import some modules. These modules are um, matplotlib, just so that we can visualize our data. Scikit-learn, um, which is where we get the module that'll perform the PCA algorithm for us, and NumPy to organize our data arrays. I'm going to start by defining standardized functions, which will uh, take any data I make and standardize it. Um, and finally, I'm going to add another function here, which I define as a basic scatter plot. I'm using this function to create from a scatter of x, a scatter of y, um, a scatter plot, and if I want to add a line to that scatter plot, um, I can do that as well. Finally, also just plotting x and y axes here, just so that it makes it easy to quickly visualize the data set. So I'm going to start by defining uh, a data set. Uh, the first, I'm going to use NumPy linspace to do it, which will create 101 of those equivalently spaced points from minus 100 to 100. And then I am going to create a randomized data set of the same length, a randomized array of the same length. And then I'm going to add the two together to create my random scatter. Finally, I also want to add one more data set or one more array to this list. That's going to be another randomized oh, set of data. Essentially, what I'm doing here is creating a scatter plot which fits to the line x equals y. And I can show that by using the scatter function that I created before, which is I need to actually redefine the x lim and the y lim here quickly, so that we can actually see the data. But yeah, this is basically a scattered approximation of the line x equals y, and you can just show the line x equals y too by just plotting NumPy linspace with itself, and the scatter expectedly well fits the line x equals y because I randomized it off the line x equals y. Finally, I am going to go ahead and standardize each of these variables. Just it doesn't really change anything with this particular data set, but when you're working with a large multivariable data set and all the data is in like different dimensions, uh, in different units, um, if all your data set is in different units, then it becomes important to make sure your data is standardized before you start doing data analysis with it. So we can see what that looks like. It's essentially the same plot, but now standardized. So the axes values, instead of going from like 150 to 150, they're going from like 2 to 2, minus 2 to 2. Next is where the fun begins, which is where we start applying our principal component analysis to the data set. So I'm just going to get rid of this line for reference first. Basically, if we ignore the fact that we just created this data off of an x equals y line, uh, we can see that the greatest amount of variability is along x equals y. Let's find out if principal component analysis can create a vector which identifies that greatest amount of variability roughly lies along the line x equals y. So we need to first rearrange the data set into an x by 2 array, uh, um, so that scikit-learn can fit that data when we get to it. Right now, a standard and C standard are both in these one-dimensional arrays, and we don't necessarily want that. So we're gonna go ahead and apply a vertical stacking to it. Where we will combine these into from separate one-dimensional arrays into a single two-dimensional array. But this is 2 by x, not x by 2, so we just transpose it. And now we have the x by 2 data set. With any principal component analysis in scikit-learn, the array needs to be x by n, where n is the number of data variables. So we will just go ahead and define that into a variable. And now we apply principal component analysis. We have called the function from scikit-learn. So we define the object and then fit our data set to that object, our n by 2 data set. And now we've performed principal component analysis. Let's see what those principal components are. To do that, we just go pca.components, and then we can view the components. And it looks like the first principal component aligns quite well with our data set. In fact, in this instance, and this hasn't happened every time I've run through this, we actually have the first principal component array aligning exactly with the line y equals x. And then the second one is going to be equal to y equals minus x. So with empirical orthogonal functions, we are constrained by the fact that they have to be all the empirical orthogonal function vectors have to be perpendicular to each other. Once you start getting into very large data sets, like 30 dimensions, 40 dimensions, those first and second EDOFs are going to both pick up on a great deal of the amount of variance in that data set. So, we can actually quantify the variance that each component of the principal component analysis explains. or the percent each EOF explains. The first EOF will have contain 99% of the variance, where the second one only contains 1%. So this is a little bit more complicated to plot. I'm not going to use the basic scatter plot I created, but we can visualize what this looks like. And this is what it looks like. Let's quickly add x lines and y-axis lines just to make this a bit cleaner for us. And we can get rid of this print statement too. But to plot each vector, I just looped through them in matplotlib. For y in components, I just defined an array of numpy zeros since these vectors are based off the origin. So the 2 points for your vectors will always be 0, 0, then xy, 0, 0, xy, and then if you're scaling to 3 dimensions, 0, 0, 0, xyz, 0, 0, xyz, 4 dimensions, 5 dimensions, so on and so forth. I can use transposed vertical stack to get these to plot again. So that's what I did to plot these lines, and we can see that the first line, x equals y, is right along the line of mode of greatest variability, and that makes sense since we originally plotted essentially a scatter around the line x equals y. So, I mentioned that principal component analysis will realign the data set, define new variables which align with the modes of greatest availability. Right now we've been plotting in x equals y, but now we can replot in the first and second principal component, and that will be uncorrelated. So we essentially get an uncorrelated data set where after we've applied a transformation of the data set, we can then, once again, using transposition to redefine the data in a way that matplotlib can read it, we now get a scatter plot that is uncorrelated, and instead of being in the space x equals y, we are now in the space PC1, PC2. We have essentially these two EOF lines up here become the new x-axis and the new y-axis. Let's now consider the three-dimensional variant. I'm selecting the original NumPy-Lin space and the two randomizations that I did for this first example of a three-dimensional principal component analysis. And then after we fit them, we can look at the explained variance again. Explained variance ratio. We can see once again, that there is one strong dominant principal component analysis, because our mode of greatest variability in this instance is still only going to be really along the line now, I guess, x equals y equals z. So what do those components look like? Oh, it's best to just straight up visualize in this case. Our empirical orthogonal functions will be three-dimensional. We can just look at it for good humor, but they're just three-dimensional EOFs. But now we can visualize what that looks like. And in 3 dimensions, we'll see one dominant vector pointing in the direction of our mode of variability, and then 2 very low variance directions, because we only have one strongly variable direction, and that's in the direction x equals y equals z. Um, the other 2 directions are basically pointing in low variance directions. Um, so we can perform transform on this data set, and we can then go ahead and plot scatters of this. And first PC1, PC2, then PC1, PC3, and once again, PC1 is the only one capturing any substantial amount of variance in the dataset. So it doesn't surprise us we don't see much straying much in the y direction again. And then plotting PC2, PC3, essentially what we're looking at, the face of this third vector, PC1, is through the page. So we basically see random scatter. If you remember at the very beginning, although you might not have noticed, I put more variance in the B dataset than the D dataset, and we can see that here with PC2 having greater variance along that direction and PC3 having less, but overall very low variance because we're basically looking in the face of the XYZ direction. Remember, principal component analysis redefines a new axis, and each of these is basically taking a slice of that new axis. I've got one more example. Right here, and we're going to use the B ABC instead of ACD. The difference here is what we're going to get is sort of like this this x equals y plane instead of an x equals y equals z line. I'll demonstrate that quickly by essentially just plotting a x equals y, an x equals z, and a y equals z plot. The faces, the 3 faces of our 3-dimensional space here, where essentially you have this sort of this is sort of a slice across the x equals y plane, this third plot here. Whereas if we were to plot xz versus yz, we see we don't see the plane at all. There's no correlation. Let's quickly fit the data set to that. Once again, we are doing standard. We're just stacking and then transposing the data set. Once again, in this case, we'll notice with the explained variance ratio that there's actually kind of 2 directions which have a little bit more variance, so that when we plot them together, we'll see that. Finally, we should grab the components with PCA components, and then we can go ahead and plot them in 3 dimensions and to visualize. For the third and final time, we are taking our principal, our eigenvectors, right, which will be three-dimensional vectors, and using them to redefine an axis along the x, y, and z when we go ahead and perform a transformation on that data. So we can do the transformation, and with this case, we have sort of like this x equals y plane, a plane along x equals y. When we plot the first two principal components, which in this case there are 2 dimensions which have the greatest variability, x, there'll be two, essentially, since we have a plane of randomized data, there's 2 dimensions which will represent it instead of one. And now, let's see if this works. Sometimes it doesn't like to work correctly. Okay, now if we look at principal component 1 plotted with 3, or principal 2 plotted with 3, we essentially just get this flat line, right? Because we're basically slicing through this plane first along sort of this uh, this principal component 2, principal component 3 dimension, and then again we're slicing along the principal component 1, principal component 3 dimension when we redefine our axes. So both of these just get plotted as essentially flat lines with nothing meaningful with them. So we've figured out, right, that all our variance here is in the plane. And I'd like to use this third example to describe what principal component analysis is not. It's not necessarily something you use it to find the directions of greatest variability. You don't use it to find where your data set has correlations. The reason why I say this is that uh, there is a correlation between A and C, but there isn't correlations between A and B and A and C, and in actuality, these are just random. When we view them this way, we just see random noise. When we view the data set this way, we view random noise. But the random noise is where our variability lies. It's in this plane where our variability lies. Rather, what we're doing here is we have essentially taken where our modes of variability are, right? These two planes of random data, and right, if we don't apply a principal component analysis to it, right, we might not identify that these 2 dimensions are the dominant dimensions when it comes to where the greatest variance in our data set lies. Obviously, with 3 dimensions, you can still plot, but once you start going higher order, 4 dimensions, 5 dimensions, 6 dimensions, 10, 20, 30 dimensions, principal component analysis ends up becoming a very powerful tool to determine if there's like only 2 or 3 variables which are contributing the most variability to the data set. When we redefine the axes, we've redefined upon the greatest variance, we simplify our data set and uh, reduce its dimensions overall. And that's a very powerful tool, because if we're thinking in 30 dimensions and we see like 20 of these types of plots, otherwise we might not be able to figure out where those modes of variability come from. It can become quite a difficult task without it. So, once again, I'm Takeshi, and this is kind of my explanation of how principal component analysis is done with Python and how powerful of a tool it can be. I hope you found this at least somewhat helpful. Uh, until next time.